Okay, so guys, give me your best attention as much as you can. Why don't we take a break close to 3? Okay, so I want to start off just making sure, but before we move forward with the grade 11 graphing stuff, I need to make sure you guys have the grade 10 graphing stuff down pat. So yesterday, our goal was more or less to talk about, do you know how to use your graphing calculator? So quick bit of review before I even get to this review. It's like a review on top of a review. Here's your graphing calculator. If you don't have one, you really, really need one. Like, I don't know how you'll actually get by, truthfully. Here's some key buttons. The y equals button. This is where you type in all your graphs. If you highlight the equals key, then it turns the graph on or off. The window button tells you what window size you have. The zoom button allows you to do a standard zoom, so you can get a picture of some of the graphs. Other useful things. Sometimes you have to wait for the graphs to show up. If you do second table, it gives you a nice little table of values. Maybe you don't like the table of values as it is. Maybe you'd like to set your table to start at 1 and go up by 8. I don't know why you'd want to, but let's say that's helpful, right? Then when you go back to your table, now it starts at 1 and goes up by 8. The last thing we need a bit of review on is if you go second calculate, value and 0 are some interesting, useful tools that we can use to try to calculate things. Today I'm going to show you guys how to do minimum, maximum, and intercept. Long story short, that was yesterday. You guys feel like you have a reasonable handle on how to use your calculators? Yeah. The more you do it, the better you get. The other advice I'm going to give you, maybe not advice so much as just a warning, there is no work to show in a lot of questions. A lot of questions, all you do is you type some stuff in your calculator, you go, the answer's 5. So I really can't have you show your work, which is both good and bad. For one, I guess, if you're not really a big fan of showing your work anyways, you're not going to lose marks. The downside, though, is when you make a mistake, it's very hard for me to help you find it. Does that make sense? So that's actually why I would suggest, if you don't have to, don't get rid of the old equations, because it doesn't hurt to still have them sitting there so we can go back and look at them later. Okay, let's do, what's up?
Do you have a metal closer here by any chance?
That's a random question. No, I don't, sorry. Okay, so these are my grade 10 notes on domain and range. I just want to make sure you guys have the concept before we go forward, so sorry if you do have it. If not, be good attention, okay? So what we're working on now is graphs. We're going to show you guys so many different kinds of graphs over the next year and a half, regardless of Dash 1 or Dash 2. Like, we do them in both courses. Dash 1, we do a few more in grade 11. Dash 2, we just do more of them in the grade 12 year instead. They push it back a year, that's all. But you still actually, all of you guys will cover almost all the exact same types of graphs. So I'm going to use this terminology a lot, input and output. Okay. What letter do we usually use for an input? X, yeah. And then for an output, you've probably been told at some point you use Y, but I want to really encourage you to get used to this notation. F of X. It means Y. It's just saying that the function has X's in the equation. That's all. If there's a relationship, we sometimes can draw this in different ways. I haven't shown this to you guys yet. Have you seen one of these before in your labs? Yeah. Okay. This is a fancy table of values. This means that you do it like this. 1 gives 2, 3 gives 2, 5 gives 7, 9 gives 8. That's all. You might ask, why did you bother writing all those values in? Well, I mean, they still exist. It just may mean that based on the values we have, we don't know whether anything actually does equal those. Maybe 2 was supposed to equal 3 and 7 was supposed to equal 5. We just didn't write them all down. Can I expect you guys to write down literally every number in the universe in a table of values? Well, that's ridiculous, right? I mean, 1, 2, 3, 4, 5, sure, that's fine. But 6 and 7 and 8 and 9, I mean, that whole table of values, if you just keep pressing down, it will go for ever. You know what I mean? What's up there?
It's like 2 Y's.
Oh, because I have multiple equations sitting there. Does that make sense? All right, back to this stuff. If you have inputs in a domain, I'm going to use that terminology. Your input is your domain, that's your X value. Your range is your Y values. And so based on the information we have, we may not actually use every single number possible. But if it has what's called a one-to-one relationship, it's considered a function. Let me see if this makes sense. 1 gives 2, 2 gives 4, 3 gives 6, 4 gives 8, 5 gives 10, 6 gives 12. Every value gave a new one, right? But here's the problem. 1 gave 2, 2 gave 4, and then I went back and wrote 1 a second time. This right here causes a bit of an issue. I can't have 1 give me 2, and then later on have 1 give me 5. Like, that doesn't work. 1 is supposed to give me just one answer. I can't give me a second one. Okay. Here's another way of drawing that. Let's say 2 gives 9, 4 gives 5, and 11 gives 5. This kind of gives us a bit of an issue here. Whereas here, 2 gives 9, 4 gives 6, 11 gives 5. See how everyone gives like a unique response? That's okay. Here's something I was using to try to illustrate with the tens when I do it this next week. Let's say that you have a relationship between how many hours you work and how much money you make. And I changed this actually. This wasn't how many hours you work. It's how many items you buy and how much it costs. I changed that. Okay, let's say you buy one thing. It costs $50, right? You guys know how like when you buy things in groups, sometimes they drop the price a little bit? Right, so then you buy 2 of them. Rather than being 100, it's 95, right? You buy them in groups of 3, it's 83. Well, wouldn't it be kind of illogical to have 7 items cost 56, but then also in the same table to say that 7 costed 55? You'd be like, well, which one is it? Does that make sense? So a function basically means if I give you 1 input, which is a domain, you get 1 output, which is a ring. You get 1 for 1. You can't have 2. Okay. Is this a function then? Well, -1 does give 2, and 0 does give 2, but here's where you'd have a problem. If this -1 gave 2 and it gave -3, that would be an issue. You can't have one number give 2. And sometimes I think the best way of illustrating this is with a vending machine. When you go to a vending machine, you input something. What do you input into a vending machine? And not just coins, but after that, you then input a button combo, right? And so I say I want the pop that's in A7. I put that input in. Does that make sense? That's like a domain. It's what you input as a value. Okay, so you enter a single code as an input to the domain of the machine, and the machine, in theory, should give you back a single item. Now, I mean, if the machine's broken and you put in $1 and somehow it gives you back like a chocolate bar and then like another one falls, I'm not talking about that because that's really cool when you get like a freebie. You know what I'm saying here? But like the way the machine is supposed to work is you type in 1 code and you get back 1 bottle of pop, not that bottle of pop plus a bonus one. You know what I'm saying here? Right? And so in terms of domain and range then, domain is all of the codes that are valid. A1 might be valid, B2 might be valid, but maybe the code Z17 isn't actually a valid code. If you try to type in Z17, the machine basically says, I can't do this, right? And your calculator will do something similar. It will give you an error code saying, well, I can't look for that because I'm not able to, right? So domain is what you input. Range then is what you output. And not all ranges are always possible. On this particular vending machine, if I want to get out of Pepsi, good luck. Because it doesn't have a Pepsi in there. Does that make sense? And so try as I may, if I try typing in every single code possible, A1, B1, C1, A2, D5, right? If I want to try to get out a Pepsi, I don't believe this machine sells Pepsi. Does that make sense? So basically my Cliff Notes version of this is if you're starting with domain and range, domain is what you input as an X value. Range is what you get back as a Y value. And they're not always all possible, which we're going to see more of today when we do quadratics. I think that'll probably do for now. These are some slides I was going to show the grade 10s here. These are some functions that eventually we're going to get to, you know, crazy looking ones where it goes wavy all over the place. Is this a function? And the answer is yes, yes it is. The reason why is something called a vertical line test. Have you ever heard of that before? Vertical line test. If you put a line straight up and down, and it only gives you back 1 point, you're golden. This is a cool graph. I want to make this one day. if you know how and you can type this into your graphing calculator, if you have a little while, you can make the Batman graph. Might take a little while. Okay. Now, this is not considered a function. Here's why. If I gave you an input of 6, let's say that I input an x value of 6. Right here is where x would be equal to 6. That's the worst line in the world, but you get the point. How many y values are there?
2.
Yeah, there's 2. And that's not good. I can't say, 6 gives me 5. Oh, by the way, and it also gives me negative 5. Right? That doesn't work for a function. So a function is you put in one answer, you get back 1. You guys can actually try typing the Batman graph.
I don't have an abs though.
I'll show you how to do that later. We're going to do that in Dash 1 in a little while. We actually will do abs. We will do that
I
later.
only do biceps.
Alright. Here's a picture I thought was kind of cool here. This kind of illustrates all these things that are functions. As I go back and forth along the x-axis there, see how there's only ever one value at a time? That's what makes it a function. So as the line goes across, these are all different kinds of functions that we will eventually learn about at some point. The only one you guys have done, though, is the linear one. So I think I've probably done enough of a review here. Let's talk about our notes for the day now. So today I want to introduce a new type of graph to your list. You know how to do a straight line. We're going to add what's called a quadratic. Okay. My starting here, though, is just referring to just the whole input-output thing. If I give you an x value, you're going to get back an f of x value, or we sometimes just call it a y. So let's start by just graphing something familiar. If I give you the rule of negative 2x plus 8, could we graph that? Let's go to the next slide. So here's negative 2x plus 8. Let me walk you through my expectations of what a graph would look like. So first thing, go to your graphing calculator to your y equals screen, and you probably have equations there. If you want to, delete them all. If you don't want to, because you want to save them for later, just turn them off temporarily and type in the new graph. It is negative 2x plus 8. All right, what should I do next? What's a good button to press at this point here? Graph's not bad, but window is better. Because who knows what my window is set to? Currently it was a good old negative 10 by 10 graph, but what if it was way off and who knows where it lands, right? The most common question kids start asking me is, Chris, I can't find my graph. And I'd go to the window and say, well, let's check it out. So a good old zoom 6 is a good idea. Because the zoom 6 goes from negative 10 to positive 10, and negative 10, positive 10. So that's one of my first requirements. I don't need you guys to actually plot this on a grid, but you do got to tell me where values are going from, okay? And then draw me what you see on your graph. So honestly, I'm okay if you don't even use a ruler, because most of the graphs we do going forward aren't even going to be straight lines. They're going to be all curvy all over the place. So I might say that it looks roughly like, I don't know, like that. Did I do it in the perfect spot? Well, no, because the next thing I'm going to ask you to do is calculate some key points for me, like plot some values on it. Like, for example, this point right here, which I probably put a little bit too low on the graph, because it probably should be a little bit higher, but that's a y-intercept, right? You guys ever in a calculator how to find a y-intercept? What are you looking for? A y-intercept is when, yeah, so you could do this. You could go to the table and look where x equals 0. And right off the bat, for me, this is no good because my table is not set nice. So the other way you can do it is go to value when x equals 0. There. Plot this as 0 and 8. Okay, clearly I have not actually drawn this at 0 and 8, but I'm okay with that because I don't need you guys to take all the time in the world to plot it out properly because we're going to make so many graphs that it's just not worth your time. If you guys are in my physics class, though, put it in the right spot. I'm not going to be okay with that. But for math right now, just tell me, yeah, this is 0, 8. We do have another intercept, right? You have an x-intercept right here, right? Do you guys remember how to find an x-intercept? An x-intercept occurs when y equals 0. If you wanted to, again, you can go to the table of values and try to figure out when y equals 0. Yeah, I didn't see it on there. But there's another tool that you can use. Second, calculate a 0. Now you have to know how your calculator works. Let me show you some things that won't work very well. Let's say that I try to do this. I'm going to press enter here, and I'm going to press enter there. And then I press enter one more time saying find me the 0, and then my calculator thinks and it gives me an error. I'm going to pick up as to why my calculator gave me that error there. Do that one more time. And the second calculate the 0, and I'm just going to put 1 right here, maybe 1 right there. There's no actual 0 between those two arrows, right? So, oops, that's not right. So make sure that it goes on the left-hand side. Make sure you clearly go past it on the right-hand side. And then one more thought. In case there's more than one x-intercept in between there, it's going to ask you for a guess. Since there's only one x-intercept here, you don't have to do much. Just make sure you press enter. Okay. So we have an x-intercept at 4 and 0. That makes sense? Right. I don't even think I'll spend much time going over the other questions here. If I want f of 2, all you got to do is find the value at 2, find the value at -1, find the value at 3. In a way, if you like the machine example, if I plug in 2 for x, what is my y value going to be? So I could go second calculate the value on x is 2. Okay, it's 4. And often we write that in a table of values, hence this whole table right here. Does that make sense so far? Okay, so let's move on. That should hopefully be more or less review. My goal now is to build on this one type of graph at a time. So, one more thought. Sorry, before I do that. We can also give you an output and have you work backwards and find an input. Okay. Here, I'm going to type in a new graph here. So, find a new spot for this. Let's say that the graph was 2x minus 4. When I graph it, and 2x minus 4 looks roughly like this. What if I ask you where... Can I close the door for you, brother? Thanks. Yeah, for sure. Yeah, we're good. Okay, let's say I ask you where it equals 6. Let's say I give you the output. Have you guys ever seen this method before? Let me walk you through it first. What you would do is you'd go to y equals. You'd say, well, we want it to also equal 6. You put a second equation on there. 1 is the original one I gave you, of 2x minus 4. The next one is of 6. And then when I graph it, you see how there's a line straight across here at 6? What I'm looking for is, well, what's this value right here? And your calculator has a way of doing that. It is called the intersect. You guys done this before? Yeah. Awesome. Cool. Okay. So second calculate and intersect. The way the intersect works is it just wants to know which graphs you want to cross. So if you go side to side, you guys see how the cursor moves side to side? If you press up or down, it toggles between all the graphs available. So essentially you have to say, this is my first curve. It uses the word curve because most graphs aren't actually straight lines. So, but I mean, this is your first graph, press enter. Is this my second graph? Sure, press enter. Press enter. One more thing though, it wants to guess. The reason why it wants to guess is what if it crosses more than one spot? Then it'll pick the closest one. But since it only crosses once, press enter. There we go. This crossed at 5 and 6. That makes sense? So then here we would actually say that x is 5. Our input was 5 to get us back a 6. That's all. You guys have seen this before? Oh, fun. Okay, so here's the new stuff then. Finally, we're at the... All of what I've done so far is really not meant to be something new, but I'm a big believer... I'll say first I'm a big believer. Did I say that last week? But I'm a big believer that I need to make sure I build a good foundation before I move onwards. So, in a way, we're now starting new curriculum. Okay? So my goal now is I want to talk about how to graph a new type of function. This is called a quadratic. Okay. And quadratics are defined by their degree of 2. Okay. Linears have x values, but the exponent on the x value, we always just write x to the 1. We don't even write the 1, right? If I give you 3x plus 4, it kind of implies there's a 1 as the exponent of the x, and we don't even write it. Now we're going to work on things that have the power of 2. And then eventually power of 3, power of 4. Does that make sense? So if it is quadratic and has a power of 2, we're kind of going back to the first unit where we talked about quadratic formulas and stuff like that. We won't do it again so much, but like there's a lot of relationship between it. So the first thing I need you guys to know is the shape. The shape of this graph is called a parabola. It's a name we give to it. One of the things you'll notice about this graph, it is not in the negatives. Yeah, do me a favor, can you close the door a little bit? It's not in the negatives. If I were to ask you about the range of this graph, let me say that again. If I were to ask you about the range of this graph, not all values of y are possible. Because I can't get a y value of -1 or -2 or -3. Right? Because what happens when you square a number? If you square -2, you get a positive. If you square -1, you get a positive. If you square 0, well, you still get 0. Is it possible to square a number and get back a negative? No. In a way, this is like my vending machine analogy. You cannot get a Pepsi out of this machine if Pepsi is considered to be like the negative values. This machine does not sell Pepsis. It sells Coke only. Coke apparently is the above axis ones, and Pepsi is the below the axis. So the first unique property I need you guys to know is that there are no negatives in this graph. It's only positive. Now, we're going to change that around a little bit later. It won't always be that way, but there is kind of a low value. And this point right here has what we call a minimum, which kind of makes sense because it's the lowest value out there, right? It's a minimum. Later today, I'm going to show you, if you don't know how to use a function called a minimum function. It'll help you find the lowest value possible. Before I do more on this, I want to point out that parabola shapes, they are so prevalent in everyday life. I want to just show you some pictures of them. Some of these are right side up, and some of them have been flipped upside down. But that sort of curvy U shape. Here is, I believe this is the St. Louis arch. And then here's just another generic arch that has that shape. I didn't realize this until my little brother became a dentist, but the inside of your teeth, of your mouth, actually has a parabola shape to it. It has that U-looking shape to it that we're going to focus on. Even a flashlight, the way that light goes out. You may have even heard of parabolic reflectors. Ever heard the word parabolic before? Basically, it means it has the shape of a parabola. Satellite dishes are actually in this sort of curvy shape. You know how like they have like a bit of an indent to them? Parabolas actually are used a ton in physics. We've used them. We just haven't used the terminology quite that much. But gravity will actually take hold and cause things to have a nice parabola shape. This time-lapse picture of the snowboarder has basically a U shape. I know it's nowhere near as like as steep as this one is right here, but if it has that sort of U shape, it's quadratic. So here's what I want to do. Let's do some more graphing. One of the best ways to practice this is just I'm going to give you some graphs and we'll graph it. And honestly, my expectations are pretty straightforward. I'm going to need another slot here, I guess. Let's try typing in x squared plus 2. I don't see any reason why I can't just keep going from -10 to +10. But if we have to change that, we'll change it later. So, type in your x squared plus 2, make sure it's a good old graph, and let's look at the graph. Does it have that sort of curvy parabola shape? It does. Except it's a bit different. It's a little bit higher. The one I showed you a few slides ago actually goes right through the origin here at 0, 0. But this one right here that I've asked you to graph is just a little bit further up. Why? What change caused the graph to move upwards? Yeah. Right, I mean, that's the only difference, right? The +2 is the manipulated variable, the only thing we changed. Well, doesn't it look like this graph is now kind of up in the sky a little bit more? That's all that happened. Right? So here's some things I'm going to require of you. Once you've got a graph, I mean, this is what I'm looking for. I'm dead serious. This would be good from my perspective. Except I need you to plot a few points. Okay. So one thing I want to do is talk about some of the key points I'm always going to want you to plot. You should always find a y-intercept. Well, to find a y-intercept, in case you're really struggling, just make the value of x be 0. It's 2. That's not the only way you can find it, but it's pretty easy. I'm also going to want you to find the x-intercepts if possible. There we go. Find me the x-intercepts if possible.
Not possible.
It isn't possible. Because x-intercepts are when y equals 0, and y equals 0 is right along this axis right here. Does this graph ever actually touch that axis? No, it's not going to happen. And this is probably the best visual way I can explain our first unit. Remember how we used the quadratic formula to solve? And sometimes the answer was, there is no answer. Now you can kind of visually see why there's no answer. I'm asking you to find something, and kind of like with the Coke Pepsi vending machine, it's not possible. For probably the last 10 years of your lives, you've been trained in math to just think that math is always, well, there's always an answer. But sometimes there are unsolvable questions where I ask you to pull this off, and then I come back and say, well, I can't. Lift this table. You might not physically be able to. Right? Throw the ball a mile in the air. I might not be able to. Right? And so that happens a lot. We usually haven't given you questions like that till now, but they're going to become more common as we go along. So, since there's only 1 point on this graph, I wouldn't give you full marks here because I want a few more points. I don't really care which other ones you give me, but find some other points to label. So I would just go to the table of values and say, yeah, you know what? I can go with, okay, actually this is not going to work. Here's my table set. Start at 0 and go up by 1s. Here, why don't I go with 2 and 6? Even though that's not actually on my graph at 2 and 6, it's close enough. And let's do one of the negatives. How about this one? -2 and 6. That'll work. When you guys draw a graph, I don't expect you to grab a graph paper. I just want you to draw it freehand on a sheet of whatever paper. Which is why I don't really care that this is not officially at 2, 6. Because you're just going to label it with a point anyways. Does that make sense? Okay. Well, let's try another one. We're just kind of exploring here. Is this still quadratic? What makes a graph quadratic? What is the defining thing in an equation that makes it quadratic?
Squared.
The squared, yeah. So because this is still squared, this should still have a quadratic shape to it. So let's just try another one. See if we can figure out some differences. So this one is x squared plus 2x minus 3 graph. Again, -10 to 10, -10 to 10. Okay. Again, here's my expectation as you graph it. I mean, try not to make it too out there, but it looks like it kind of comes down like this, goes through there, comes up through there. Does it still have our good old parabola shape? Yeah. Nice little U shape to it. Only there's a difference now. Now we're actually allowed into the negatives. Before we weren't, but now it's actually possible. And one of the reasons why it's possible is due to that -3 right there. Because whatever values you have, you're now taking away 3 by the time you're done. So now you can actually get into the negatives. Let's plot some key points again, just for practice. You guys are going to be using your calculators a lot this year. So, do we have an x-intercept? We have 2 x-intercepts actually. So I would expect you to plot both x-intercepts, and it also looks like there's a y-intercept in there as well. So, however it is that it works for you in your calculator, some kids, they'll go right to the table. And they'll say, hey look, -3 gives a y a 0, perfect. And 1 gives a 0, perfect. That was easy. Okay, what if it's not on a whole number though? There are other ways of solving, right? You could go second, calculate the 0, and then kind of go on the left and on the right and kind of narrow down a little range right there. So you could use that function as well to solve for it. To find the y-intercept, just plug in when the value is 0, that'll work. There's actually one other way for you guys to know what the y-intercept is, and it depends on, I guess, what you learned last year. Do you guys know what a constant term is? You heard that terminology before? What's a constant term? Okay. Constant term is the one that does not have a variable. See how this right here has a variable? This one right here has a variable, but this one right here does not have a variable. Okay. A constant term is your y-intercept. Here's the reason why. Remember how a y-intercept is when x is equal to 0? Well, if this guy right here has a variable, and x is 0, then this is basically gone, because it's 0, right? If this term right here also has a variable, but again, x has to be equal to 0, then this is gone. Well, the only thing left then will be the number that doesn't have a variable, so minus 3. So sometimes you don't even need to use your graphic calculator to figure out a y-intercept. You just look at whatever the constant term is, and that's your y-intercept. So far, so good? Let's try another one. I made a subtle tweak to this one here. Very, very subtle. The only thing I changed is that some of the negative and positive signs are different. It's now negative x squared minus 2x plus 3. That's the only change I've made. What's weird about this graph? Upside down. Anyone want to hazard a guess as to why this graph is upside down? What change did we make to put it upside down? It's a negative, yeah. You guys would have learned last year about something called slope. You guys remember like slope is y mx plus b kind of thing there? Okay, in grade 10, we kind of tell you a partial truth, and we call it slope. But there's a better word for it. So I want you guys to start using that this new definition. This is known as a leading coefficient. Have I used that word yet? You guys, are those words yet with you? Leading coefficient? Okay, long story short, whatever term is first, whichever one has the highest variable, so the x squared one, if it is positive, we say it has a positive slope. Last year you guys learned slope means it goes like uphill, right? And if it had a negative, it goes downhill. Well, the same thing applies to this one here. Whatever your leading value is, effectively it changes your slope. Only we don't call it a slope, we just call it a leading coefficient now. So if it's a negative, it makes your graph go upside down. If it's positive, your graph is a normal smiley face. That's all. So just like with slope, this value right here can affect the direction of the graph. Okay. If it's okay with you guys, in the interest of saving time, could you calculate these x and y intercepts? Do you feel comfortable knowing how to do it? Okay. I mean, if you want me to do it again, but I mean, really, it's just rinse, lather, repeat, like you're doing the same thing over and over. The point I wanted to make, the whole reason I have this slide in here, if you have a negative, flips the graph upside down, that's all. So here's what we're going to do. Similar to linear functions, I need you guys to be able to find an output if I give you an input. If I give you an input, can you find me an output? Or vice versa, if I give you the output, could you give me an input? So let's try a few more examples. Here's our equation. X squared minus 6x plus 5. If I give you an x, could you get me a y? Or if I give you a y, could you get me an x? So let's start by graphing this one. X squared minus 6x plus 5. Alright, if I want to see where this thing equals negative 3, here's a couple options I have. I could go to my table and try to figure out whether this thing ever equals negative 3. Hey, look. I found that it equaled negative 3. It equaled negative 3 twice, though. That's okay. This actually doesn't make it not a function anymore. See how this thing still passes the vertical line test? That's still okay. You can't have one x give two y's, but you can have one y give two x's. That's actually allowed. So at negative 3, I didn't draw this very well, but it looks like negative 3 right about here. I should draw it a little bit lower. There's two answers. 2 gives negative 3. Oh, that's really not. Let's make that better. Let me start from the top, actually. Okay, where's that guy? There. Alright. So it looked like 2 gave negative 3. But the other location that gave negative 3 was 4 giving negative 3. You guys remember how with the quadratic formula, sometimes you could have 2 answers? Here we have 2 answers. What if I ask you where it equals negative 4? Can it equal negative 4? Yeah, it looks like it equals negative 4 right about there. Look, negative 4 is at 3 with negative 4. But will this thing ever get as low as negative 5?
No.
I don't think so. Here, I can even prove this to you. Watch. I'm going to go to my y equals screen. Let's check my cursor. There it is. I'm going to go to my y equals screen, and I'm going to put a line on there at negative 5. I'm going to put a second line on there. And then look. Do they cross?
No.
No. Here, watch one more thing, Eden. Let's try to intersect them. If I go second calculate, the intersect, and I say, here's my first graph, here's my second graph, and I'll just press enter for the guess. Watch the calculator. These little lines up in the corner here, by the way, mean the calculator is thinking. And eventually it gives me another error saying, I cannot find where they cross because the answer is they don't. Does that kind of help make sense a little bit of our first unit with the quadratic formula? How you can have 2 answers, 1 answer, or no answers? When we get further into this, not this unit, but eventually you guys will learn about graphs that look like, say, this. And if I asked you where it equaled 2, let's say this was where it equals 2, you'd actually say there are 1, 2, 3, 4, 5 answers maybe. So sometimes there is not even just 0, 1, or 2 answers. Sometimes there could be 3 or 4 or 5. Eventually, you'll learn about a graph where there's actually infinity answers. There's an infinite number of right solutions. So, but we'll build up little by little. How am I doing so far? Are you guys still with me? Why don't we take a quick break here because I still got so much more to do. I want to make sure you guys are still focused. So take 10 is right now. When this clock down here gets to 3:02, I'll start again. Okay? So you got 4 minutes. 3:02 on this clock down here.
BE doesn't let senior highs use those computers. No, it's already going ahead.
Everybody's on their phone. Like literally every single one, I think, is on their phone.
That's good. Yeah. Is that your little handbag? Yeah. You got any mints or anything? Any snacks? Right? 3, 2, 1. I have lotion. Hey, Jacob. I get free truck, I guess. I got free car, I guess.
Alright. Guys, before I go on here, is this, I need to gauge so I know, because I don't know how much you guys learned last year. Is this pretty familiar?
Yeah. Pretty familiar. A little bit.
Okay. Honestly, that's really good, because once you get the basics of how functions work, really all I need to do as we go along and learn more and more is just kind of introduce a new one and say, hey, look, check out the pattern on this one. This one looks really cool. Alright, and eventually you learn, graphs that do, I'll show you some of the ones we'll learn. Eventually you'll learn about a graph that does this, a graph that does this, a graph that does this. Eventually, if you really want to, I can show you how to make circles. Or it's actually possible to make a heart graph. Or if you really want to go crazy, make the Batman symbol or however you pull it off. Okay. The only problem though with these last three, these ones right here, not functions. They're still graphable, they're still equations, they're just not a function because for one x value you can get back two y values, that's all. We still work with them though. Okay, why don't I finish off here then with what I haven't covered. So find this next slide here. I think it's the next one. I think I just skipped a slide. Okay, I need to talk about a bit more terminology then for these graphs that are called parabolas. Okay, so the name of a quadratic graph is called a parabola, and where it's located is very important because there could be 0, 1, or 2 solutions. You could say have 2 solutions right here. You could say have 1 solution right here. If you were looking for when it crosses down there, it may not never cross that. Okay. This point right here is so important. The base of the parabola is so important. It has a very special name. It's called a vertex. I just need you guys to know that name, called the vertex. It doesn't matter whether the vertex, guys, give me a focus, okay? Just give me a break for a second, okay? I probably only need 15 minutes. The base of that parabola, either the lowest point or the highest peak, it doesn't really matter, but it's called a vertex because really it controls whether or not you're going to have something cross 1, 2, or 3, or 0 times. Okay. The other thing I need you guys to know is the term called a line of symmetry, or in your guys' work, I'm going to ask you to find an axis of symmetry. It's the same sort of concept. The axis of symmetry is the imaginary line that goes exactly through the middle of this graph, because it's always kind of symmetrical. It always folds over on itself. If I ask you for an axis of symmetry, it's always written as an equation. The equation is going to be x equals something. Anyone want to hazard a guess? It's going to be in this one here. What is the middle line? Not 0, because 0 would be right here. 1. 1, yeah. Yeah. So if I ever ask you for an axis of symmetry, you need to find this vertex, figure out where it's going through, and it's just x equals whatever that point is. Right? So on this one, it's 1. That's all. So what I want to show you guys now then, if you haven't already figured this out, is if I give you a graph, we need to sometimes find that location, that vertex point. So let's, really, here's a vertex, which is a maximum. Here is a vertex, which is a minimum. So what I want to work with now is just remind you, or show you, I guess, how to use the minimum and maximum buttons on your calculator, because that's a useful tool to have. Let's find an example. Here we go. Find this example here. We may have even done this one before. X squared plus 4x plus 5. So I'm kind of running out of slots. Figure that one out. x squared plus 4x plus 5. Wait, first question here. How do I know it's quadratic? Because it's x squared, right? If I give you x cubes or x to the 1, it's just not quadratic. That's all. But we will eventually add more and more to our list, right? So graph this thing from -10 to +10, -10 to +10. Looks like it's somewhere in this vicinity over here. Let's say that we want to try to find this vertex right here. Well, I'm sure most of you can kind of figure this out on your own, but here's how it would look. Go second, calculate. Is that going to be the lowest or highest point? Well, it's the lowest point, right? So you use the minimum. And essentially the way this works is you put the cursor on the left and on the right of wherever you're looking for. So you need to kind of put the cursor way over here past the lowest point. So I did that. Then scroll it around to over here. And then in case there's more than one location where there's kind of a lowest value, you should kind of put the cursor about where you think it is and press enter. And there's your minimum. Okay, this is a really important talking point. In order for your calculator to calculate this minimum value, it uses calculus and goes through some sort of really crazy formulas that I can't even imagine, let alone explain to you guys. But the reason why this matters is that everyone's calculator, believe it or not, is going to calculate this a little bit differently. Mine says -1.999997.
Me too.
Anybody have one that says something slightly different than the 97s though? So you have 2.00001, right? And you just have literally 2. So, oh, it's 2.00002. Yeah. So everyone's calculator may do this a little differently. It depends on what model number you have. You have to be smarter than your calculator and recognize that that number right there is not -1.999997 or -2.0002. Use your common sense. That value is -2. Does that make sense?
Yeah.
So, and this is just based on the fact that your calculator is doing some pretty high-tech calculus in a blink of an eye to find that value for it. When you guys eventually take calculus in grade 12, I can actually show you how your calculator is doing this. But that's another year and a half away.
Okay, let's do it.
Well, I gotta teach you another year and a half with the math first. Gotta build up. So, long story short, guys, if your calculator spits out something strange like -1.9997, use your common sense and say that this minimum value is -2 and 1. That's all. So I know I have some different questions to ask here, but I'd like to walk through some of the things I'm going to ask you for on a test question. So for example, I might ask you for the x-intercepts. Go. Tell me the x-intercepts.
None.
Around 10, yeah, good.
It's right here.
Okay. I might ask you for a y-intercept.
Where's that one?
You could use your calculator.
I'm not going to get
Or you could remember that Mr. Shalk once taught you about what a constant term is. There you go. Your y-intercept is 5.
do it.
Or, in case you totally forgot that, find the value when x is 0, and ta-da, it's at 5. I may as well plot that even. Does anybody else have an assignment in front of them? Doesn't really matter whether it's -1 or -2. There's a question on there where I asked you to graph things, and there's like 8 different bullet points of things you have to look for. There's like intercepts, vertexes. What else is on that list of things?
Range, degree, turning point.
Okay, let me do them one at a time here, okay? Jake, read out the first one for me.
Intercept.
Okay, so intercepts. You guys are okay on how to find an intercept here? We have a y-intercept, we don't have x-intercepts. Wait, what's next?
Domain.
Okay, so domain is all of the valid input numbers. Let's go back to the vending machine example. Are there any number combinations that I can't type into the vending machine? Are there any x values that I can't use? And I know that sounds very strange right now, because any x you can use if you want. If I want to look for x being -5, I look for -5. If I want x to be 1,000,000, it's on there somewhere. I just have to make my window big enough. So in an example like this, domain, we write it in this format. X is an element of the real numbers. Have you seen that before?
Yeah.
Yeah? Okay. For the most part, all of the graphs you're going to learn this year, the domain is always that. There's almost always x element of the reals. You can use any value you want. However, going forward, that's not always true. There are sometimes certain inputs that you can't use for whatever reason. Okay. You know what? I think it's worth my time to show you this. Eventually, you're going to learn about what's called a square root graph. Here, I'll throw a new one in here. Eventually, you guys will all learn about a square root graph. And the square root graph looks like this. It actually literally starts right here and keeps going forward. There are no values over here in the negatives. Why? Can you square root a negative number? So it actually means you have an invalid input. If I were to go to my table of values on this particular graph, the square root graph, I can't square root -1. I can't square root -2. I can't square root -3. So it gives me an error. And so sometimes you'll discover that literally there is no x value that you can work with. Okay. But for the most part, on the graphs you guys are working with, I really should have deleted this one. It's almost always x as element of reals. All right. The next one is range. Is every y value possible? Can you get a y value of 17? Yeah, it's way up here. I think we get 2x's way up there. Y value of 5? Sure, that'll work. What about if I asked you for a y value of -10 way down here? No. Okay, so here's a good example of how the range is not y as an element of the reals. Here's the answer. I'll give it to you, and then you guys can see whether it makes sense to you. That's how we write the range. Y is greater than or equal to -2. How do I figure that out? See how that -2 right there? Oh no, I did that wrong. Sorry. I did it wrong. Y has to be greater than or equal to 1. I screwed this up. It's because of this 1 right here. Sorry if I screwed you up there. Okay. Why does that have to be bigger than that 1? Well, that 1 is the lowest this thing ever gets down to. Okay. So on quadratic graphs, you're always writing y is greater than or less than a certain value, and you need to find that vertex to find your range. All right, let's say I asked you for the axis of symmetry. Thank you. Okay, the axis of symmetry, this is why I was screwing up. The axis of symmetry will be the other value. See how this graph can be literally cut right in half down the middle here? Where is it getting cut in half? Not the y value. The y value I already used, but the x value of -2. That's the axis of symmetry. You write it as an equation. So x is -2. I lost my border. Jake, what else is on that list there that you were telling me? What have I missed? Domain range.
Degree.
Okay, degree. Well, we've already talked about that. The degree of this graph is 2 because it is a square. Okay, what else is on there?
Turning points.
Okay, turning points. Turning point is a generic word that I will use for any time the graph turns around. For you guys, so far, because we really haven't gotten that far, the graph is only going to turn around right here at the vertex. But eventually, you're going to learn about graphs where it does something like this. And now it turns around right here, and here, and here, and here. But since we're working with kind of our base level quadratics right now, there's only the one turning point. It's your vertex. What else?
Axis of symmetry.
We covered that one. Okay. Okay, the last one's called an asymptote. That only is going to apply to the -1 kids, and we haven't learned that function yet, so we'll get to that one. So I think I write on that question there, if applicable, not all of these things actually apply, because there may not be an asymptote. There may not be an axis of symmetry. There may not be x-intercepts. Not everything actually has to exist. So.
Then there's end behavior.
Oh, end behavior. Thank you. Okay, let's talk about that. Do you guys know your quadrants? Quadrant 1, 2, 3, 4?
Yeah.
This is quadrant 1. No. This is quadrant 2. quadrant 3, quadrant 4. You guys know these? Okay, if I ask you for end behavior, it would look something like this. End behavior will be starting in quadrant 2, the most negative inputs you have begin in quadrant 2, and then the most positive inputs you have would end in quadrant 1. You guys see how here it starts, as we go like from left to right, it starts here in quadrant 2, and it ends over here in quadrant 1. That makes sense? As we learn more and more graphs, that'll change. For example, if I give you a linear graph like this one started in quadrant 3 and ended in quadrant 1. This graph here started in quadrant 2 and ended in quadrant 4. Okay. It's even possible for us to have graphs that start in quadrant 4 and end in quadrant 1. So that's your end behavior. How do the extremes work? Is that the list there, Jake? Is anything?
It doesn't say what the
Anybody else have that list there? Did I cover all the ones that were on that list for the assignment there?
Yeah.
Okay, cool.
I said the last one.
Okay. Okay, last thing here. I think I'm done for the day. I'm just going to quickly cover the last slides here, but I've done most of this. I need you guys now to know on your calculator how to find an intersection. Find where things cross. Hopefully you know how to do that. I need you to know how to find a minimum or a maximum to find where things cross. Because essentially what I'm going to ask you to do is sketch a graph of any equation. I'm not going to do this one. But what if I give you a graph where they weren't all nice even whole numbers? What if they were crazy decimal numbers?
That was crazy.
I mean, when you look at your table of values, it's very unlikely that they're now going to be, you're going to look at a table of values and find those. But if you know how to use your calculate function, you can use values, zeros, maximums, and intersects to find whatever you're looking for. See where we're going with that? So ultimately, this is what I need you guys to be able to do. Plot a graph, find where these things intersect, and they may intersect at irrational values, like 1.42866, etc. I just need you guys to round it at a certain point. I don't actually care where you round it, just round it at like 1.4 or 1.43. I feel like you guys are both done for the day. Okay. Okay, we'll just go to this very last slide and then I'll call it quits. So here's kind of the summary. Most of what we do going forward here is I give you a graph and I ask you to figure out things like, well, which way does it open, up or down? Where's the vertex? Where's the max and the min? What's the axis of symmetry? What's your x and y intercepts? What's your domain and range? Okay, that's a very typical question. If you guys have your practice journals, you guys have these guys nearby still maybe? You do?
I did.
Okay. When you get to the back pages here, there's a whole bunch where it'll say things like graphing exponential functions, graphing logarithmic functions, graphing polynomial functions, graphing linear, graphing quadratic. Okay. Slowly over time, we're going to learn how to graph all of those. For you guys in my -2 class, just due to the amount of time we have, I'm not going to give you guys practice journal questions. But for you guys in -1, I am going to have you guys do a little bit of practice journal questions over time. It's actually good. It's an easy way to get a high mark, isn't it? How many of you guys got a really good mark on your practice journal last time we did it? It should be hard. Okay, I feel like I've covered what I need to. Do you guys have questions of me? Okay, one last thought, guys. I've discovered that me being a little bit loosey-goosey and letting you just do your assignments whenever you want to, doesn't always work for everybody. So I mentioned this last day. Your first assignment is due Thursday. I have one more lesson tomorrow. I'm hoping it's only about half the class. And then you guys have a little bit of time today. You have Wednesday sometime, and then all of Thursday. But I want you guys to be on a more rigid schedule, because when you fall behind, it puts you in such a hole, right? I mean, you guys probably are aware of this. When you fall behind on your assignments and you get off track, then you're always fighting to catch up. So I'm going to make your first assignment due Thursday. Okay?
On the website, we only have one thing.
Yeah, I've only posted 1 of 10. I'll post the next one next week. Okay, sound good? So, guys, I know a lot of you took off yesterday with 15 minutes left. I would do something with 15 minutes, okay? Because it's 15 minutes. You can probably get at least a question done. Okay, Is there some left? Yeah, here we go.
So, the previous one,
Yeah.